There's a vast, calm region of space that Earth is slowly drifting through right now, and almost nobody who isn't a professional astronomer has ever heard of it. It doesn't have a dramatic name in the popular imagination, no fire, no collision, no explosion. It's simply an absence. A place where there is less of everything than there should be. Less gas, less dust, fewer galaxies, fewer clusters of galaxies, less of the raw material that the universe is built from. And the strange part is that this absence might be quietly distorting some of the most careful measurements cosmologists have ever made. To understand why an absence could matter so much, it helps to slow down and look at the universe the way astronomers actually see it. Once you strip away the tidy diagrams from textbooks. For a long time, the popular picture of the cosmos was something like a jar of scattered sand, stars and galaxies sprinkled more or less evenly through space in every direction. That picture is comforting in its simplicity, but it isn't how the universe is actually arranged. When astronomers began mapping the positions of hundreds of thousands and eventually millions of galaxies in 3 dimensions, a very different structure emerged. Galaxies are not scattered evenly. They are gathered into long filaments and broad sheets, and those filaments and sheets connect at nodes where enormous clusters of galaxies sit, bound together by gravity. Between these filaments and walls lie huge, roughly spherical regions that are almost, though never quite, empty. Astronomers call these regions voids, and the whole arrangement, filaments, walls, clusters, and voids together, is often called the cosmic web. It's a genuinely strange thing to sit with. If you could shrink yourself down and hover above a 3-dimensional map of the nearby universe, you would not see a uniform haze of galaxies. You would see something closer to a sponge, or a foam, or the inside of a soap bubble bath, with thin, glowing strands of matter wrapping around dark, mostly empty chambers. Some estimates suggest that these voids take up somewhere close to 90% of the volume of the universe, even though they contain only a small fraction of its matter. Almost everything we can see and touch, in a cosmic sense, galaxies, stars, gas clouds, dark matter halos, is concentrated into that remaining 10% or so, the walls and threads of the web. The voids are the vast, quiet spaces in between. It's worth pausing here to say a little more about what exactly is doing the gravitational work of pulling this structure together. Because it isn't just the ordinary matter, the stars, gas and dust that astronomers can see directly. Careful measurements of how fast stars orbit within galaxies, and how galaxies move within clusters, have shown for decades that there simply isn't enough visible matter to account for the gravity holding these systems together at the speeds observed. Something else, invisible to telescopes across the entire electromagnetic spectrum, from radio waves to gamma rays, but still gravitationally influential, appears to make up the bulk of the universe's total matter content. Astronomers call this unseen substance dark matter, and while its exact particle nature remains one of the biggest unanswered questions in physics, its gravitational effects are measured with considerable confidence through galaxy rotation speeds, through the way galaxy clusters bend light from more distant objects behind them, and through its clear fingerprint in the pattern of fluctuations in the cosmic microwave background. Current estimates suggest dark matter outweighs ordinary, visible matter by a factor of roughly 5 to 1 across the universe as a whole. It's dark matter, more than ordinary matter, that provides most of the gravitational scaffolding shaping the cosmic web, with ordinary matter, the stuff that eventually forms stars and galaxies and, eventually, planets and people, simply falling into the gravitational valleys that dark matter carves out first. When cosmologists run the large simulations described later in this account, tracking how the cosmic web assembles itself over billions of years, it's overwhelmingly the gravitational behavior of dark matter that they're modeling, with ordinary matter treated as an important but secondary participant, following dark matter's lead into the same filaments, walls, and voids. This structure didn't spring into existence all at once. It grew slowly out of tiny irregularities in the density of the early universe. In the first fractions of a second after the Big Bang, the universe was, as far as anyone can tell, almost perfectly smooth, with only extremely faint ripples in density from place to place, differences of only a few parts in 100,000. Those ripples might sound too small to matter, but gravity is patient. Regions that started out just slightly denser than average pulled in more matter over time, growing denser still, while regions that started out slightly less dense lost matter to their denser neighbors, growing emptier still. Over billions of years, this slow process of gravitational amplification turned tiny differences into the dramatic contrast we see today. Dense filaments and clusters on one hand and vast echoing voids on the other. Computer simulations that model this process, starting from the faint density ripples imprinted in the early universe and running forward through cosmic time, reproduce the web-like structure we observe with remarkable fidelity. It's one of the true triumphs of modern cosmology that a theory built from a handful of numbers can predict, in broad outline, the shape of the entire visible universe. The first hints that galaxies weren't randomly scattered came gradually. Through the 1970s and 80s, as astronomers began the painstaking work of measuring not just the positions of galaxies on the sky, but their distances from us as well, using a technique called redshift surveying. Because the universe is expanding, light from distant galaxies is stretched toward longer, redder wavelengths, and the amount of that stretching, the redshift, correlates with distance. By measuring redshifts for large numbers of galaxies, astronomers could build genuine three-dimensional maps, rather than flat, two-dimensional pictures of the sky. One of the earliest and most influential of these surveys was carried out at the Harvard-Smithsonian Center for Astrophysics, led among others by the astronomer Margaret Geller and her colleague John Huchra, along with contributions from Robert Kirshner and others working on related projects. When the results came in during the early 1980s, they revealed something startling: an enormous, nearly empty region in the direction of the constellation Boötis, stretching for hundreds of millions of light years, with only a handful of galaxies found inside it. It became known as the Boötis Void, sometimes nicknamed, half-jokingly, the Great Nothing. At the time, its existence was almost hard to believe. Nothing in the simple models of the universe then in fashion predicted structures on that scale. But as more surveys followed, and as computing power grew enough to simulate structure formation in detail, voids of this kind turned out to be not a strange exception, but a normal, expected feature of how matter organizes itself under gravity over cosmic time, before those larger surveys came along, though there was an important scientific argument still being settled in the background, one that shaped how astronomers interpreted every one of these discoveries. Through much of the middle of the 20th century, the Big Bang model, the idea that the universe began in an extremely hot, dense state and has been expanding and cooling ever since, competed for scientific acceptance with a rival idea called the steady-state theory, championed most prominently by the British astronomer Fred Hoyle, along with Hermann Bondi and Thomas Gold. The steady-state theory proposed that the universe has no beginning and no end, that it has always looked roughly the same on average, with new matter continuously created to fill in the gaps left by expansion, keeping the overall density constant across all of cosmic time. It was a serious, carefully worked out theory, and for a while it had real observational support, including some early galaxy counts that seemed at least broadly consistent with either picture. The decisive evidence against it came from two directions: the discovery of the cosmic microwave background in 1965, which the steady-state theory had no natural way to explain, since a universe that never had a hot, dense beginning wouldn't be expected to have any such leftover afterglow, and separately, growing evidence that the population of galaxies and quasars visible at great distances, and therefore from a much earlier point in cosmic history, looked measurably different from the population found nearby. Evidence of genuine cosmic evolution over time, which a truly unchanging steady-state universe wouldn't predict. By the 1970s, the Big Bang model had become the clear scientific consensus, and it's within that now well-established framework that all the later discoveries about the cosmic web, voids, and the expansion rate took shape. With the Big Bang model firmly established, cosmologists turned their attention to working out the details of exactly how structure, the filaments, walls, clusters, and voids of the cosmic web actually grew over cosmic time. And this required computer simulations sophisticated enough to track the gravitational evolution of enormous numbers of particles over billions of simulated years. One of the most influential of these efforts was the Millennium Simulation, carried out in the mid-2000s by an international collaboration. which modeled the gravitational evolution of roughly 10 billion particles, representing dark matter, within a cube of simulated space more than 2 billion light-years across, starting from realistic initial density fluctuations matching those measured in the cosmic microwave background, and evolving them forward according to the equations of gravity across the equivalent of nearly the universe's full age. The resulting simulated structure, filaments, clusters, and voids emerging naturally from those initial small fluctuations matched the general appearance of the observed cosmic web remarkably well, offering strong support for the basic lambda CDM picture of how structure grows. Later, even more ambitious simulations, including the Illustris project and its successor Illustris TNG, added in the complex physics of ordinary, visible matter as well, not just dark matter, modeling gas dynamics, star formation, supernova explosions, and the feedback effects of supermassive black holes at galaxy centers, producing simulated universes whose galaxies, and the cosmic web those galaxies trace out, look startlingly similar to the real thing when compared side by side. These simulations have also been essential for understanding the physical mechanism by which voids grow emptier over cosmic time relative to their surroundings, since the process, while intuitive in outline, involves some subtle physics worth spelling out a little further. Within a young universe still relatively close to uniform, a patch of space that starts out with even a slightly below average density experiences slightly weaker inward gravitational pull than the cosmic average, simply because there's slightly less matter nearby to do the pulling. That means matter within an underdense patch tends to drift outward, toward the surrounding, relatively denser regions at a rate slightly faster than the universe's overall average expansion rate. This isn't a special force pushing voids apart. It's simply the ordinary gravity-driven flow of matter responding to the density differences already present. Crucially, this process is self-reinforcing. As matter drifts out of an underdense region, that region becomes even less dense than before, which weakens its already weak internal gravity even further, which causes matter to drift out even faster in a slow, steadily accelerating feedback loop that plays out over billions of years. Meanwhile, matter accumulating in the surrounding denser filaments and walls makes those regions denser still, strengthening their own gravity and further accelerating the whole process. Over enough cosmic time, this feedback loop is what carves the initially mild density differences present in the early universe into the dramatic contrast seen today. Deep, nearly empty voids surrounded by sharply defined, massive walls and filaments. The discovery of the Boötes void itself has a nice human story behind it worth telling in a little more detail. Robert Kirshner, along with graduate students and collaborators including Augustus Oehmler and Paul Schechter, had originally set out simply to measure redshifts for a modest, carefully chosen sample of galaxies scattered across the sky, part of a broader effort to understand how galaxies were distributed in 3 dimensions, rather than just as points on a flat, 2-dimensional map. When they attempted to select galaxies in the direction of Boötes for their sample, they found, to their considerable surprise, an almost total absence of galaxies within a certain range of redshift, and therefore within a certain range of distance, across a large area of sky. Their first instinct, reasonably enough, was to suspect some kind of instrumental problem or a mistake in their target selection. It took repeated, careful follow-up observations to confirm that the gap was real, an enormous, genuinely underdense region of space rather than an artifact of the survey. The eventual estimate that the void spans somewhere in the range of 250 to 330 million light-years across made it, at the time of its announcement in 1981, the largest such structure ever identified, and it prompted a wave of both excitement and healthy skepticism throughout the astronomical community, since existing theories of structure formation at the time struggled to explain how a region that large and that empty could have formed within the age of the universe. Later, far larger surveys like the 2-degree field Galaxy Redshift Survey, carried out using the Anglo-Australian telescope through the late 1990s and early 2000s, and eventually measuring redshifts for over 200,000 galaxies, and the Sloan Digital Sky Survey, which began operations in 2000 using a dedicated 2-point, 5-meter telescope in New Mexico and went on to measure redshifts and detailed properties for several million galaxies and quasars over the following 2 decades, mapped out the positions of hundreds of thousands and eventually millions of galaxies, filling in the picture in far greater detail. These surveys didn't just confirm that voids like Boötes were real, they revealed that the entire observable universe, out to distances of billions of light years, is threaded through with this same web-like arrangement. Filaments and walls of galaxies wrapping around underdense chambers. At every scale, these surveys were able to probe. Additional infrared surveys, including the 2-micron all-sky survey, usually called 2MASS, and later the 6-degree field galaxy survey, extended this mapping effort further, particularly useful for filling in regions of sky partially obscured by the dust and stars of our own galaxy's disk, the same zone of avoidance that had long complicated efforts to fully characterize structures like the Great Attractor. These maps confirmed and extended the cosmic web picture, revealing dozens of voids of varying sizes woven through the local universe, some relatively modest, spanning tens of millions of light years, others enormous, spanning hundreds of millions. It's within this broader context, a universe now understood to be structured like a web, riddled with underdense chambers, that a particular and unusually large void, one that seems to include our own cosmic neighborhood, entered the conversation. Before turning to that void directly, it's worth understanding exactly where we sit in the universe's larger architecture, because it helps explain why a nearby underdensity would even be worth worrying about. Earth orbits the Sun, one ordinary star among roughly 200 billion or so in the Milky Way galaxy. The Milky Way itself is not isolated. It belongs to a small collection of gravitationally bound galaxies called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies spanning a region a few million light years across. The Local Group, in turn, sits near the outskirts of a much larger structure called the Virgo supercluster, sometimes described as our local supercluster, centered on the massive Virgo cluster of galaxies, tens of millions of light years away. But even the Virgo supercluster turned out, in a discovery announced in 2014 by a team led by the astronomer R. Brent Tully, to be just one lobe of an even grander structure, which the team named Laniakea, a Hawaiian word meaning something like immense heaven. Laniakea is a supercluster containing roughly 100,000 galaxies, spread across a region so vast that light takes hundreds of millions of years to cross it. The team defined its boundary not by counting galaxies, but by tracing the direction that galaxies are moving under gravity, essentially watching which way the currents of cosmic matter flow, and drawing the boundary where those currents diverge, flowing toward different central concentrations of mass. At the gravitational heart of this flow lies something called the Great Attractor, a massive concentration of matter, partially hidden from view behind the plane of our own galaxy, whose gravity is subtly tugging on the entire local group and much of the surrounding supercluster. This matters because it tells us that our motion through the universe is not simple. We are not just sitting still while space expands uniformly around us. Astronomers can measure the local group's motion relative to the cosmic microwave background, the faint afterglow of the Big Bang that fills the sky in every direction, and finds a surprisingly large speed, several hundred kilometers every second, on the order of 1,000,000 kilometers an hour. This motion shows up as a subtle temperature difference across the sky in the cosmic microwave background, warmer in the direction we're moving toward, cooler in the direction we're moving away from, an effect called the CMB dipole. Part of this motion is attributed to the pull of the Virgo cluster and Laniakea's Great Attractor. But some cosmologists have long suspected that part of it might also be explained by something else entirely. The possibility that we are not just being pulled toward a massive structure, but also being gently pushed, so to speak, out of an underdense one. The underdense one is what's sometimes called the KBC Void, or the local hole, named for the astronomers who did much of the key work characterizing it. Ryan Keenan, Amy Barger, and Lennox Cowie, whose 2013 study first drew wide attention to just how large and how deep this local underdensity might be. Their analysis, using infrared observations of galaxies across large areas of sky, suggested that the density of galaxies in our surrounding region falls significantly below the cosmic average, and that this underdense region might extend for an extraordinary distance, on the order of 2 billion light years across, making it, if the estimate holds up, one of the largest voids ever proposed. dwarfing even earlier discoveries like the Biota's Void by a wide margin. According to their estimate, the density of matter within this region might be depressed by something like 20 to 50% below the average density of the universe as a whole. An enormous deficit if accurate, though the exact figures remain debated and vary considerably between different studies and different methods of measurement. It's worth pausing here and being honest about the state of the evidence, because this is exactly the kind of claim that deserves care rather than certainty. The existence of an underdensity in our general cosmic neighborhood is not seriously disputed. Multiple independent lines of evidence, including galaxy counts, measurements of the way light from distant supernovae is dimmed or brightened by intervening structure, and studies of the way galaxies are moving do seem to point towards some kind of local deficit. What remains genuinely uncertain is exactly how large, how deep, and how significant this particular void is. Some studies using different data sets and different statistical techniques find evidence for a substantial local underdensity roughly consistent with the KBC Void description. Other studies, using different assumptions or different traces of the matter distribution, find much smaller or more ambiguous effects, or struggle to reproduce a void of the claimed size within standard models of how structure grows in the universe. Computer simulations built on the standard cosmological model, the one cosmologists refer to as lambda CDM, tend to predict that voids as large and as empty as 2 billion light-years across should be quite rare. Rare enough that finding one right around our own location would be something of a statistical surprise, though not an impossibility. This tension between what simulations predict and what some observations seem to show is itself an open and actively studied question, rather than a settled discrepancy in either direction. To understand why any of this connects to one of the biggest open problems in cosmology, it helps to step back and revisit the history of how astronomers first realized the universe was expanding at all, and how they've tried to measure the rate of that expansion ever since. The story begins in the early 20th century, when the American astronomer Vesto Slipher, working at Lowell Observatory in Arizona, began measuring the spectra of what were then called spiral nebulae, fuzzy patches of light whose true nature was still unknown. Slipher noticed that the light from most of these nebulae was shifted toward the red end of the spectrum, a redshift suggesting they were moving away from us, and generally at surprisingly high speeds. At the time, nobody was entirely sure whether these spiral nebulae were relatively nearby clouds of gas within our own galaxy, or entire separate galaxies, island universes, far beyond the Milky Way. That question was resolved in the 1920s, largely through the work of the American astronomer Edwin Hubble, using the powerful 100-inch telescope at Mount Wilson Observatory in California. Hubble identified a particular type of pulsating star, called a Cepheid variable, within the Andromeda Nebula, and was able to use its pulsation period to estimate its true brightness and therefore its distance. This technique relied on earlier, crucial work by the astronomer Henrietta Swan Leavitt, working at the Harvard College Observatory in the early 1900s, who discovered that Cepheid variable stars pulse at a rate directly related to their intrinsic luminosity, their true brightness, rather than how bright they merely appear from Earth. Brighter Cepheids pulse more slowly, fainter ones more quickly, and the relationship between the two is precise enough to use as a kind of cosmic ruler. If you know a star's true brightness from its pulsation period, and you measure how bright it appears from Earth, the difference tells you how far away it must be, since light dims in a predictable way with distance. Leavitt's discovery, sometimes called the period luminosity relation, quietly became one of the most important tools in the history of astronomy, even though she received relatively little recognition for it during her own lifetime. Using Leavitt's relation, Hubble calculated that Andromeda lay far, far beyond the edges of the Milky Way, definitively establishing that it, and the other spiral nebulae, were entire separate galaxies in their own right, comparable in scale to our own. This alone was a revolutionary result, expanding the known universe overnight by many orders of magnitude. But Hubble didn't stop there. Combining his own distance measurements for a number of galaxies with Slipher's earlier redshift measurements, and building on important theoretical work already being done by the Belgian priest and physicist Georges Lemaître, who had independently proposed in 1927 that the universe was expanding based on Einstein's equations of general relativity, Hubble found something remarkable, published in 1929, The farther away a galaxy was, the faster it appeared to be receding from us. This relationship, now known as Hubble's law, was the first direct observational evidence that the universe itself was expanding. That space between galaxies was stretching over time, carrying galaxies apart from one another like dots painted on the surface of an inflating balloon. The constant of proportionality in Hubble's law, describing exactly how much faster a galaxy recedes for every unit of additional distance, became known as the Hubble constant, and pinning it down precisely has occupied astronomers for the better part of a century since. Hubble's own original estimate, based on the limited and somewhat imprecise distance measurements available in the late 1920s, was quite far off from modern values, roughly 500 kilometers per second per megaparsec, a unit describing kilometers per second of recession speed for every megaparsec of distance, with a megaparsec being roughly 3,026,000 light years. Over the following decades, as measurement techniques improved, as astronomers identified and corrected various systematic errors in the cosmic distance ladder, and as bigger and better telescopes came online, that estimate came down substantially, eventually settling, by the early 21st century, into a range clustered somewhere around 70 kilometers per second per megaparsec, though even that seemingly settled range concealed a persistent and puzzling disagreement between different methods that has only sharpened with time. To understand that disagreement, it helps to understand the two broad families of techniques astronomers use to measure the expansion rate today, since they approach the problem from almost entirely different directions, using almost entirely different physics, and yet are expected, if our understanding of the universe is correct, to arrive at the same answer. The first approach, often called the early universe method, looks at the cosmic microwave background, the faint relic radiation left over from roughly 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time, allowing light to travel freely through space rather than being constantly scattered by free electrons. This radiation was first detected, somewhat by accident, in 1965, by two researchers at Bell Labs, Arno Penzias and Robert Wilson, who were troubleshooting a persistent, unexplained background noise in a radio antenna they were using for satellite communication research, after ruling out various mundane explanations, including, memorably, pigeon droppings inside the antenna. They realized they had detected the actual afterglow of the Big Bang itself, a discovery that earned them the Nobel Prize in Physics and provided dramatic confirmation of the Big Bang model over its main rival at the time, the steady-state theory. In the decades since Penzias and Wilson's accidental discovery, a series of increasingly sophisticated space telescopes have mapped the cosmic microwave background in ever greater detail. The Cosmic Background Explorer, launched by NASA in 1989 and generally known by its acronym COBE, was the first to definitively detect the tiny temperature fluctuations across the sky predicted by theories of structure formation, a result announced in 1992 that was significant enough to earn its lead scientists, John Mather and George Smoot, the Nobel Prize in Physics in 2006. COBE's map, however, was fairly coarse, blurring together large patches of sky and unable to resolve fine structure. The Wilkinson Microwave Anisotropy Probe, launched in 2001 and usually referred to as WMAP, improved on this dramatically, mapping the cosmic microwave background with far sharper resolution over 9 years of observation, allowing cosmologists for the first time to measure the basic parameters of the standard cosmological model, the relative amounts of ordinary matter, dark matter and dark energy, and the universe's overall geometry with real precision. The European Space Agency's Planck satellite, launched in 2009 and operating until 2013, went further still, mapping the cosmic microwave background at even finer angular resolution and across a wider range of frequencies, allowing for better separation of the genuine cosmic signal from foreground contamination caused by dust and gas within our own galaxy. It's Planck's final, most refined analysis of this data, released in stages through the mid-2010s, that produced the precise 67 kilometers per second per megaparsec figure for the Hubble constant that anchors one side of the modern tension, revealing not just its overall temperature, an almost perfectly uniform 2.725 degrees above absolute zero. But tiny temperature fluctuations across the sky, differences of only a few parts in 100,000, that encode a wealth of information about the early universe. These fluctuations arise from sound waves, literally pressure waves that ripple through the hot, dense plasma of the early universe before the moment when light was set free, leaving behind a characteristic pattern of hot and cold spots of particular preferred sizes, an effect known as baryon acoustic oscillation. By carefully analyzing the statistical pattern of these fluctuations, and combining that analysis with a theoretical model of how the universe has evolved since, cosmologists can extrapolate forward across nearly the entire history of the cosmos and predict what the expansion rate ought to be today. This method, when applied to the most recent and precise Planck satellite data, yields a Hubble constant of approximately 67 km per second per megaparsec, with an impressively small uncertainty. The second approach, often called the local or late universe or distance ladder method, doesn't rely on any assumptions about the early universe at all. Instead, it works its way outward step by step through the nearby cosmos, using a chain of overlapping distance measurement techniques, each one calibrated against the one before it, which is why it's called a ladder. The first rung uses geometric parallax, measuring the tiny apparent shift in a star's position against distant background stars as Earth orbits the Sun. A direct and essentially assumption-free way of measuring distance for stars close enough for the shift to be detectable. Space telescopes like Hipparcos and more recently Gaia have measured parallax distances for enormous numbers of nearby stars, including Cepheid variables in our own galaxy, allowing astronomers to calibrate Leavitt's period luminosity relation with high precision, with Cepheids calibrated using parallax. The next rung uses those Cepheids to measure distances to nearby galaxies that also happen to host a particular kind of exploding star called a Type 1 supernova. These supernovae occur when a white dwarf star, the dense, burnt-out core left behind after a star like the Sun exhausts its nuclear fuel, either pulls in enough additional matter from a companion star or merges with another white dwarf, pushing its mass past a critical threshold known as the Chandrasekhar limit, at which point it becomes unstable and detonates in a runaway thermonuclear explosion, briefly outshining an entire galaxy. Because this explosion is triggered at a fairly consistent mass threshold, these supernovae tend to release a remarkably consistent amount of energy, making them useful as what astronomers call standardizable candles, objects whose true brightness can be inferred, with the help of certain corrections based on how quickly the explosion brightens and fades, closely enough to use as reliable distance markers, even across billions of light years, far beyond the reach of Cepheid measurements alone. It's worth lingering for a moment on the physics of that critical mass threshold, the Chandrasekhar limit, since it's such a beautiful piece of 1930s physics and it's the reason Type 1a supernova are so consistent in the first place. The Indian-American astrophysicist Subrahmanyan Chandrasekhar worked out, as a young graduate student traveling by ship from India to England in 1930, that there was a maximum possible mass for a white dwarf star, roughly 1.4 times the mass of the Sun, beyond which the quantum mechanical pressure of tightly packed electrons, the only thing normally holding a white dwarf up against its own gravity, would no longer be sufficient to prevent further collapse. Below that limit, a white dwarf is stable indefinitely, slowly cooling and fading over billions of years. At or above that limit, something dramatic has to happen instead. When a white dwarf in a binary system slowly gains mass from a companion star, or when two white dwarfs spiral together and merge, and the combined mass creeps up toward that Chandrasekhar threshold, the core becomes hot and dense enough to ignite runaway carbon fusion throughout the star nearly simultaneously, unbinding the entire star in a single tremendously energetic explosion within a matter of seconds. Because this always happens at very nearly the same mass threshold, the resulting explosions tend to release very nearly the same total amount of energy each time, which is exactly the property that lets astronomers use them as standardizable candles across billions of light years of the universe. Chandrasekhar's own theoretical work on this subject was initially met with considerable skepticism from some of the most senior astrophysicists of his era. including a notably harsh public dismissal from Arthur Eddington, one of the most respected astronomers of the time, and it took decades before Chandrasekhar's calculations were fully vindicated and widely accepted, eventually earning him the Nobel Prize in Physics in 1983. A reminder that even well-reasoned, mathematically sound ideas in astronomy sometimes have to wait a long time for the observational evidence and the scientific community's confidence to catch up. By finding galaxies close enough to have both a measured Cepheid distance and a Type 1a supernova, astronomers can calibrate the supernova's true brightness, and then use that calibration to measure distances to much more remote galaxies that host similar supernovae but are too far away for Cepheids to be visible at all. Combining these calibrated supernova distances with the redshifts of the host galaxies gives a direct empirical measurement of the expansion rate in the relatively nearby present-day universe. No extrapolation from the early universe required. This local method, most prominently championed over the past couple of decades by a research group led by the astronomer Adam Rees, using data from the Hubble Space Telescope and, more recently, the James Webb Space Telescope, has consistently yielded a Hubble constant of approximately 73 km per second per megaparsec, again with a fairly small uncertainty, but stubbornly and persistently higher than the 67 or so obtained from the early universe method. It's worth noting that this local measurement effort, often referred to by the name of the research collaboration behind much of it, such 0ES, standing for supernovae, H0, for the equation of state of dark energy, has been a decades-long undertaking. Adam Rees, who shared the 2011 Nobel Prize in Physics for earlier work, alongside Saul Perlmutter and Brian Schmidt, demonstrating that the universe's expansion is accelerating rather than merely continuing at a steady pace, has led much of this later effort to measure the present-day expansion rate with ever-increasing precision, steadily adding more calibrating galaxies, more observed Cepheids, and more careful corrections for subtle effects like interstellar dust and the slightly different chemical compositions of stars in different galaxies. Rather than resolving the tension as precision improved, as many researchers initially expected and hoped, the gap between the local and early universe measurements has, if anything, become statistically sharper over the past decade as the uncertainty on each individual measurement has shrunk. In the mid-2010s, when the tension was first being taken seriously as a real puzzle rather than a statistical curiosity, the disagreement between methods sat at a significance level that could still plausibly be explained by chance, or by some modest as yet uncorrected systematic effect. By the early 2020s, with data from the Gaia satellite refining the parallax calibration of Cepheid variables, and with dozens of additional calibrating galaxies and supernovae added to the local sample, the statistical significance of the disagreement climbed to the point where a chance fluctuation became extraordinarily unlikely, which is part of why the puzzle has increasingly shifted within the research community. From a question of whether the tension is real to a question of what specifically is causing it. At first glance, a difference between 67 and 73 might not sound dramatic, a difference of roughly 9%. But in the world of precision cosmology, where each method claims an uncertainty of only a percent or two, a 9% gap between two independently measured values, using two completely different sets of physics and two completely different eras of cosmic history, is enormous, statistically far too large to be dismissed as ordinary measurement noise. Cosmologists have calculated that if both methods are correctly measuring their stated uncertainties, the odds of this particular gap arising purely by chance are exceedingly small, often quoted as being less than 1 in a million, sometimes expressed by statisticians as exceeding what's called 5 sigma significance, a threshold conventionally treated in physics as strong evidence that something real, rather than a statistical fluke, is going on. This puzzle has come to be known as the Hubble Tension, and it has become one of the most actively debated, open problems in modern cosmology. The reason this matters so much goes beyond simple curiosity about a single number. The expansion rate of the universe is deeply woven into the entire framework cosmologists use to describe the history and structure of the cosmos. It affects calculations of the universe's age, since a faster current expansion rate, all else being equal, tends to imply a somewhat younger universe when you run the expansion backward in time. It affects estimates of distances to remote objects, since much of astronomy's distance scale ultimately rests on the value of the Hubble constant, and it's tightly connected through the equations of general relativity to other fundamental properties of the cosmos, including the density of matter, the density of dark energy, and the geometry of space itself. A discrepancy this significant suggests that either there's a subtle, undiscovered error lurking somewhere in one or both measurement techniques, or more excitingly and more unsettlingly, that there's some genuine new physics missing from the standard cosmological model. Physics that behaves differently in the early universe than the simple picture currently assumes. Both possibilities have attracted serious attention. On the side of measurement error, researchers have spent years hunting for subtle systematic biases that might inflate or deflate one of the two results. Could the calibration of Cepheid variables be subtly off? Perhaps because of interference from nearby stars crowding the images. Or because Cepheids in different galaxies have slightly different properties depending on their chemical composition. Could there be an unaccounted for bias in how Type 1a supernovae are selected or corrected? Could the theoretical model used to interpret the cosmic microwave background be missing some subtle physical effect? Extensive cross-checking, using independent techniques such as gravitational lensing time delays, in which the bending of light around massive foreground galaxies creates multiple images of a background quasar that flicker at very slightly different times. Or using an entirely different kind of standard candle called the tip of the red giant branch, based on a well-understood point in the life cycle of aging stars, has generally supported both results independently, making a simple, single-point measurement error look increasingly unlikely as a full explanation, though not entirely ruled out for every possible subtle contribution. On the side of new physics, cosmologists have proposed a wide range of speculative modifications to the standard model that might help resolve the tension. One family of ideas, sometimes grouped under the term early dark energy, suggests that dark energy, the mysterious force behind the universe's accelerating expansion, might not have had a perfectly constant strength throughout cosmic history, but instead had a brief additional boost of strength in the early universe before fading away, which would subtly shift how the cosmic microwave background data is interpreted and could help reconcile the two Hubble constant values. Other proposals involve tweaking the properties of neutrinos, ghostly, nearly massless particles produced in huge numbers by the Big Bang, whose exact masses and interactions remain only partially understood, and which play a subtle role in the physics that shapes the cosmic microwave background. Still, other researchers have explored more exotic possibilities, including modifications to the fundamental theory of gravity itself, departures from Einstein's general relativity on cosmic scales, though these tend to face significant challenges, reproducing all the other successes of the standard cosmological model simultaneously. None of these proposals has yet achieved anything close to consensus support, and most cosmologists regard the Hubble tension as still genuinely unresolved, an open problem rather than a solved mystery with a favored answer. It's within this landscape of competing explanations that the idea of a local void enters the conversation, offering a comparatively modest, non-exotic possible contribution to the puzzle, one that wouldn't require any new fundamental physics at all. Just a better accounting of our own particular location within the universe's lumpy structure. The core of the idea works like this. The local distance ladder method for measuring the Hubble constant relies on measuring the redshifts, and therefore the apparent recession speeds of relatively nearby galaxies, generally within a few 100 million light-years, close enough for Cepheid-calibrated Type 1a supernovae to be usable as distance markers. But the redshift of any individual galaxy isn't a pure measurement of the universe's overall expansion. It's a combination of two things added together: the genuine cosmic expansion, stretching space uniformly everywhere, and something called peculiar velocity, the galaxy's own additional motion through space, caused by the gravitational pull of nearby structures, on top of and separate from the expansion itself. Usually, for galaxies far enough away, peculiar velocities are a small, correctable nuisance compared to the much larger effect of cosmic expansion. But if we happen to live inside or near the edge of an unusually large, underdense region, then many of the nearby galaxies used to calibrate the local Hubble constant measurement might share a common, systematic peculiar velocity, all being gently pulled along with us, out of the void and toward the denser surrounding structure, in a shared outward flowing current, sometimes called a bulk flow. If that shared outward flow exists and hasn't been fully accounted for, it would make nearby galaxies appear to be receding slightly faster than the universe's true underlying expansion rate alone would produce, which would bias the local distance ladder measurement of the Hubble constant to come out artificially high, potentially explaining some or all of the gap between the local measurement of about 73 and the early universe measurement of about 67. It's an elegant idea specifically because it doesn't require inventing any new particle or modifying gravity. It simply asks whether the standard assumption that our particular corner of the universe is a representative, average sample of cosmic density might be wrong, and asks what happens to the numbers if it is. Several research groups have tried to estimate how large this effect could plausibly be, given various estimates of the KBC Void size and depth, and the results vary considerably depending on the assumptions used. Some analyses suggest the local void, if it's as large and as deep as the more generous estimates propose, could account for a significant fraction, though probably not the entire gap in the Hubble tension, perhaps explaining somewhere in the range of a few percent of the roughly 9% discrepancy, leaving a smaller but still meaningful residual tension that would still require some other explanation. Other analyses, using more conservative estimates of the void's properties, or using different simulation techniques to model the resulting bulk flow, find the local void contributes only a very small, almost negligible correction, essentially concluding that even if the void is real, it's not nearly large enough to resolve the tension on its own. The honest summary, as of the most recent research, is that the local void hypothesis remains a live, actively studied possible partial contributor to the Hubble tension, but not a generally accepted full solution, and certainly not something treated as settled fact within the cosmology community. It sits alongside measurement systematics and new physics as one of several candidate explanations still being weighed against one another, with new data expected to help narrow things down considerably in the coming years. Part of why the debate has been hard to settle comes down to a genuinely difficult technical challenge. Distinguishing a galaxy's peculiar velocity from the universe's overall expansion requires extremely precise, independent distance measurements for very large numbers of galaxies spread across enormous volumes of space, which is exactly the kind of survey that has historically been expensive and time-consuming to carry out. It also requires reconciling observations with theoretical predictions from computer simulations of how structure grows under gravity, starting from the known initial density fluctuations. And here too, there's genuine tension worth being upfront about. Some of the largest and most detailed cosmological simulations built on the standard Lambda CDM model run on some of the world's most powerful supercomputers, using enormous grids of simulated particles representing dark matter and ordinary matter evolving under gravity across billions of simulated years, tend to have real difficulty naturally producing voids quite as large and as deep as the more extreme KBC Void estimates suggest, without some additional ingredient or a lucky, unusually large statistical fluctuation. This doesn't necessarily mean the void isn't real, since simulations, however sophisticated, still involve simplifications and limited resolution and rare. Unlikely structures do occasionally happen even within a correct theory, but it does mean the void's existence, at the largest proposed scale, remains an active point of scientific disagreement rather than settled consensus, and no interesting and somewhat more radical alternative to the simple bulk flow picture, worth mentioning for completeness, comes from a body of work sometimes called inhomogeneous cosmology, pursued by researchers including the physicist David Wiltshire, who has proposed something called the timescape model. Rather than treating the local void as simply producing an extra peculiar velocity on top of an otherwise perfectly uniform cosmic expansion, this approach suggests that the uneven distribution of matter throughout the universe, dense clusters here, empty voids there, might mean that time itself passes at very slightly different effective rates in different regions, according to the equations of general relativity, and that this effect, summed up over the whole observable universe with all its lumps and voids, could subtly change how the overall expansion of the universe should be interpreted, potentially offering an alternative explanation for some cosmological puzzles without requiring the mysterious dark energy at all. This remains a minority position within cosmology, and most researchers in the field continue to find the standard picture. Uniform expansion plus a separate, gravity-driven peculiar velocity effect from real structures like voids to be a more straightforward and better supported description, but it's a reminder that the relationship between local structure and the interpretation of cosmic expansion is subtler and still being actively debated at a foundational level than the simple textbook picture sometimes suggests. Stepping back from the technical debate for a moment, it's worth sitting with just how strange the underlying situation is. Regardless of exactly how it eventually gets resolved, we are potentially living inside a bubble, cosmologically speaking, a region of space significantly emptier than the universe's overall average, surrounded at a great distance by denser walls of galaxies and dark matter. If this is correct even in outline, it changes something about how we should think about our own vantage point. It's a gentle but genuine echo of earlier revolutions in astronomy, each of which quietly demoted Earth, and then the Sun, and then the Milky Way, from some presumed position of cosmic centrality to something more ordinary, a particular unremarkable location among countless others. Copernicus removed Earth from the center of the solar system. Later astronomers, including Harlow Shapley in the early 20th century, showed that the Sun wasn't at the center of the Milky Way either, but out in one of its spiral arms. And Hubble's own work, discovering that the Andromeda Nebula was a separate galaxy entirely, showed that the Milky Way itself was just one galaxy among countless others, rather than the entirety of everything that exists. A large local void, if confirmed, would be a smaller, subtler version of the same pattern, not a demotion in size or importance exactly. Since voids are common cosmic features rather than remarkable achievements, but a reminder that even our broader neighborhood, spanning hundreds of millions or billions of light years, might not be a representative, typical sample of the universe as a whole, and that this local peculiarity might be subtly coloring some of our most careful measurements of the cosmos beyond it. There's also a gentler, more speculative thread worth mentioning, one that the researchers themselves tend to treat with appropriate caution. If we do happen to live in an unusually underdense region of the universe, it would likely mean a somewhat quieter cosmic environment than average, fewer nearby galaxy mergers, fewer close encounters with other large structures, potentially calmer conditions overall on very large scales, simply because there's less surrounding mass to stir things up gravitationally. Whether this has any meaningful bearing on the conditions that allowed life to arise here is almost impossible to say with any confidence, since the vast majority of factors relevant to a planet's habitability, the type and age of its star, the composition and orbit of the planet itself, the presence of a stabilizing moon, the history of asteroid and comet impacts, the particular chemistry available in that pocket of the galaxy, are governed by processes on scales of individual stars and planetary systems, utterly dwarfed by anything happening on the scale of a void a billion light years across. Most researchers who study habitability treat any connection between the large-scale cosmic environment and the emergence of life as, at most, a very distant, weak, and largely unproven consideration, worth noting as an intriguing possibility, rather than treating as any kind of established explanation for our own existence. There is, admittedly, a somewhat more grounded and better studied version of this general idea, operating at a much smaller scale than an entire cosmic void, worth mentioning for contrast. Astronomers have long discussed the concept of a galactic habitable zone, the notion that certain regions within a galaxy, like our own, might be more conducive to the long-term stability required for life to develop than others. Regions too close to the crowded, turbulent center of a galaxy tend to experience more frequent close stellar encounters, more intense radiation from the supermassive black hole typically found there, and a higher rate of supernova explosions nearby, any of which could periodically sterilize or disrupt a developing biosphere. Regions too far out toward a galaxy's edge, meanwhile, tend to have lower abundances of heavier elements, the products of previous generations of stars and supernovae, which are necessary building blocks for rocky planets and for the chemistry of life as we understand it. The Sun's location, roughly 2/3 of the way out from the center of the Milky Way's disk, in a relatively quiet, unremarkable region between two of the galaxy's spiral arms, is sometimes discussed as a reasonably comfortable middle ground by this reasoning, though like the void hypothesis discussed above, This remains an area of ongoing research and reasonable scientific debate rather than settled consensus. And it operates on a scale of tens of thousands of light years, the size of a galaxy, rather than the billion light year scale of a cosmic void, which is worth keeping distinct, even though both ideas share a similar underlying logic. That where you happen to sit within a larger structure might quietly shape what's possible for the life that develops there. Before turning to what's actively being done to settle these questions, it's worth spending a little more time on some of the other pieces of the story, because the history behind each measurement is almost as interesting as the puzzle itself, and understanding it helps explain why cosmologists trust these numbers as much as they do, even while they argue over the small but stubborn gap between them. Start with the question of how anyone first noticed that our own cosmic neighborhood might be moving in some coordinated, unusual way in the first place. In the 1980s, a group of 7 astronomers, working together so closely and so productively that they became informally known as the 7 Samurai, a nod borrowed from the well-known film, set out to measure the distances and motions of a large sample of elliptical galaxies in our surrounding region of the universe. Led by Donald Lynden Bell, along with colleagues including Alan Dressler, Sandra Faber and others, the group used a relationship between a galaxy's rotation or velocity dispersion and its intrinsic brightness to estimate distances independent of redshift, allowing them to measure each galaxy's peculiar velocity, its motion beyond simple cosmic expansion. What they found, published in a series of papers around 1987 and 1988, was that a large number of galaxies across a wide swath of the sky appeared to share a common streaming motion, all moving in roughly the same direction at several hundred kilometers per second, as though being pulled by something massive lying beyond them. They named this hypothetical unseen mass concentration the Great Attractor, and calculated that it lay in the general direction of the constellations Centaurus and Norma, partly obscured from view by the dense band of stars and dust along the plane of our own galaxy, a region of sky sometimes informally called the zone of avoidance because it's so difficult to observe clearly from Earth. For years, the exact nature and extent of the Great Attractor remained mysterious, precisely because so much of the relevant sky lies hidden behind our own galaxy's obscuring disk. Eventually, using infrared and X-ray observations capable of piercing through galactic dust more effectively than visible light, astronomers identified a massive cluster of galaxies called the Norma cluster, sitting roughly in the right location and at roughly the right distance to account for a substantial part of the observed pull. But later, wider surveys revealed that the Great Attractor itself is not the ultimate source of the motion, but rather one massive stepping stone along the way to an even larger structure lying farther beyond it, the Shapley supercluster, one of the most massive concentrations of galaxy clusters known in the nearby universe, roughly 650 million light-years away, whose combined gravitational pull appears to be responsible for a significant share of the local group's total motion relative to the cosmic microwave background. This layered picture, smaller structures nested within the gravitational influence of larger ones stretching out to greater and greater distances, turned out to be a preview of the same kind of layered, hierarchical organization that the later Laniakea supercluster mapping would reveal on an even grander scale. It's worth being clear that the Great Attractor and the Shapley supercluster describe an overdensity, a place with unusually large concentrations of mass pulling matter toward it, which is a distinct concept from the underdensity described by the local void, or KBC Void, discussed earlier, even though both concepts are involved in explaining the same overall observed motion of our galaxy through space. In fact, one intuitive way to think about the two together is that they represent opposite sides of the same coin. Matter in our region of the universe appears to be flowing away from relatively empty regions, like the local void, and toward relatively dense ones, like the Great Attractor and the Shapley supercluster. Exactly the kind of gradient in gravity that the void hypothesis described earlier depends on to generate its outward bulk flow. There's also a related, though technically distinct, structure worth mentioning to avoid confusion, since the terminology in this area can get a little tangled. Astronomers also use the term local void to refer to a separate, considerably smaller, and much closer, underdense region lying just on the other side of the local group from the Virgo cluster, a relatively nearby void whose gravitational influence has been studied by Tully and collaborators as a contributor to the small-scale motions of galaxies within a few tens of millions of light years of us. This nearby local void is a genuinely different structure from the much larger, more distant KBC Void discussed throughout most of this account, even though both are sometimes casually described using similar language, and both, interestingly, appear to be pushing on the local group's motion in a broadly similar direction, away from underdensity and toward the denser structures beyond. The existence of multiple nested voids and overdensities at different scales, all subtly contributing to our galaxy's total measured motion, is a nice illustration of just how layered and complicated the true structure of the nearby universe turns out to be once you look closely compared to the simple single number that a measurement like the local group's total speed relative to the cosmic microwave background might suggest at first glance. Returning to the question of the distance ladder itself, it's worth adding a little more detail about the rungs beyond Cepheid variables and Type 1a supernovae, because astronomers have developed several independent techniques precisely so that they can cross-check one against another, catching subtle errors that might otherwise go unnoticed if only a single method were ever used. One such technique relies on a different kind of pulsating star called an RR Lyrae variable, generally older and somewhat fainter than Cepheids, but useful because they're found in older stellar populations, including the outer halos of galaxies, offering an independently calibrated standard candle. Another technique relies on measuring distances to a particular class of galaxy called the tip of the red giant branch, based on a well-understood, sharply defined point in the life cycle of aging, lower mass stars, where a star's core reaches a specific temperature and density threshold that triggers a sudden runaway ignition of helium fusion, producing a characteristic, easily identifiable brightness that varies very little between different stars, making it useful as another type of standard candle. This one calibrated somewhat differently from Cepheids and requiring different assumptions, and therefore useful precisely because it's vulnerable to different potential sources of error. Measurements of the Hubble constant using the tip of the red giant branch method, carried out by researchers including Wendy Friedman and collaborators, have tended to land in a middle position, somewhat lower than the Cepheid supernova result and somewhat higher than the cosmic microwave background result, adding yet another layer of nuance to the overall puzzle rather than clearly resolving it in favor of either extreme. Yet another entirely independent technique, developed more recently, relies on measuring the distances to certain galaxies using naturally occurring measures, essentially the microwave equivalent of a laser produced by water molecules in dense gas clouds orbiting close to the supermassive black holes at the centers of some galaxies. By observing how the orbital motion of this gas changes over time, extremely precise geometric distances can be calculated for the handful of galaxies where such megamasers happen to be visible. Most famously the nearby galaxy NGC 4258, providing a valuable geometric distance measurement that doesn't rely on Cepheids, supernovae, or any of the usual stellar standard candles at all, and offering yet another independent cross-check on the overall distance scale. Perhaps the most conceptually elegant independent method, though technically demanding to carry out, uses something called gravitational lensing time delay. When a massive foreground galaxy happens to lie almost exactly along the line of sight between Earth and a much more distant, brightly variable object, typically a quasar, its gravity bends the light from that distant object into multiple separate images, arriving at Earth along slightly different paths of slightly different length. Because the quasar's brightness naturally flickers over time, astronomers can watch for the same flickering pattern to appear in each of the lensed images, but delayed by a certain number of days or weeks depending on which image it appears in. That time delay, combined with a careful model of the foreground galaxy's mass distribution, gives a way to calculate distances geometrically based on the bending of light itself rather than on any calibrated standard candle. A collaboration called H0LICOW and its successor collaboration TDCOSMO applied this technique to a handful of suitable lensed quasar systems through the 2010s and found results generally consistent with the higher local distance ladder value of the Hubble constant, providing yet another independent line of evidence supporting the reality of the tension. Since it's hard to imagine the same systematic error affecting Cepheids, supernovae, and gravitationally lensed quasars all in exactly the same way and by exactly the same amount. Taken together, this growing collection of independent techniques, Cepheids and supernovae are our library variables, the tip of the red giant branch, water megamasers, and gravitational lensing time delays, each relying on different physics, different assumptions, and different potential sources of systematic error, has made it progressively harder to argue that the Hubble tension is simply the product of one single, overlooked mistake in one particular method. Several methods, using largely independent physics, continue to cluster around the higher, local value, while the early universe method, using an entirely different kind of physics rooted in the cosmic microwave background, continues to yield the lower value, which is precisely why so many cosmologists have shifted over the past several years toward taking seriously the possibility that some genuinely new physics, some correction to the standard cosmological model's treatment of the early universe, or some meaningful contribution from local structure, might be required to fully explain the gap, rather than expecting it to simply dissolve once yet another decimal place of precision is added to any single measurement. On the theoretical side, it's worth adding a bit more detail to some of the proposed new physics solutions mentioned earlier, since they illustrate just how creative and how carefully constrained this kind of theorizing has to be. The early dark energy proposals, developed in detail by researchers including Vivian Poulin, Tristan Smith and collaborators, suggest introducing a new component of energy that behaved like dark energy, exerting a repulsive, expansion-driving effect, but only briefly, around the time when the universe was still dominated by radiation, before ordinary matter came to dominate the total energy budget, and then this early dark energy component would need to fade away almost entirely, well before the era captured in the cosmic microwave background's later, more detailed structure. Such a component, if it existed, would subtly change the size of what's called the sound horizon, the maximum distance those early pressure waves in the primordial plasma could travel before the universe became transparent, which in turn changes how the cosmic microwave background data needs to be interpreted when extrapolating forward to today's expansion rate, potentially nudging the early universe method's answer upward toward the local method's higher value. The challenge with these models, and with most other proposed new physics solutions, is that they need to be carefully tuned to fix the Hubble tension without breaking any of the other things the standard cosmological model already explained successfully, including the detailed pattern of the cosmic microwave background's temperature fluctuations at other scales, and the observed clustering of galaxies on large scales. And so far, most detailed early dark energy models, while not ruled out, haven't provided a fully satisfying, unstrained fit to all the available data simultaneously, leaving the door open but not conclusively walked through. A related family of ideas focuses on neutrinos, the extremely light, weakly interacting particles produced in enormous numbers during the first fraction of a second after the Big Bang. The exact number of distinct neutrino types and their exact masses are not perfectly pinned down by particle physics experiments, and small adjustments to these properties can subtly shift how the cosmic microwave background data needs to be modeled, since neutrinos affect the way that early pressure waves are propagated through the primordial plasma. So far, changes to neutrino properties large enough to meaningfully help with the Hubble tension tend to run into tension with other independent constraints, including direct laboratory measurements of neutrino masses and separate cosmological measurements of large-scale structure, making this avenue interesting, but like early dark energy, not yet a fully satisfying standalone solution. Modifications to gravity itself represent a more radical category of proposed solutions, and it's worth mentioning one well-known example, called modified Newtonian dynamics, or MOND, originally proposed by the physicist Mordechai Milgram in the early 1980s, not primarily to address the Hubble tension, which wasn't yet recognized as a distinct puzzle at that time, but to explain a much older problem: why the outer regions of spiral galaxies rotate faster than the visible matter within them seems able to account for, using standard gravity without invoking any unseen dark matter at all. Mond proposes that the law of gravity itself departs slightly from Newton's and Einstein's standard formulations at extremely low accelerations, of the kind found in the outskirts of galaxies, which would allow visible matter alone to explain observed rotation speeds without dark matter. While Mond has had some success explaining certain galaxy rotation patterns, it has struggled considerably to explain other lines of evidence for dark matter, including the detailed structure of the cosmic microwave background and the way galaxy clusters bend light through gravitational lensing. And most cosmologists consider standard dark matter, combined with the standard lambda CDM model, to remain a far better supported overall description of the universe, even though Mond and related modified gravity theories continue to be studied and refined by a smaller community of researchers, including occasional applications to the Hubble Tension specifically, generally without achieving anything close to the same level of support as the standard explanations already discussed. Turning to what's actively being done to settle these open questions. Several major astronomical projects currently underway or recently launched are expected to sharpen our understanding considerably over the coming years. The dark energy spectroscopic instrument known as DESI, mounted on a telescope at Kitt Peak National Observatory in Arizona, has been measuring the redshifts of tens of millions of galaxies and quasars since its survey began in the early 2020s, constructing by far the largest and most detailed three-dimensional map of the universe's large-scale structure ever assembled. Data that will be invaluable for characterizing the true size, depth, and boundaries of any local underdensity with far greater statistical confidence than earlier, smaller surveys allowed. The Vera Rubin Observatory, situated in Chile and beginning its main decade-long survey in the mid-2020s, is expected to observe billions of galaxies across the southern sky repeatedly over 10 years, providing not just a static map but a record of subtle changes over time, useful for measuring peculiar velocities and bulk flows with unprecedented precision. The European Space Agency's Euclid mission, launched in 2023, is mapping the distribution of galaxies and, crucially, the distribution of dark matter through its gravitational lensing effects across a huge swath of the sky, aiming to pin down the properties of dark energy and the geometry of the universe with far tighter constraints than currently available, which will also feed directly into resolving how much of the Hubble tension might be attributable to local structure versus something more fundamental. Meanwhile, the James Webb Space Telescope, since beginning science operations in 2022, has already been used to measure Cepheid variable stars and Type 1a supernovae in galaxies with far greater clarity than was possible from the ground or even from the earlier Hubble Space Telescope, helping to rule out at least some of the more mundane possible sources of measurement error in the local distance ladder method. Since Webb's sharper infrared vision reduces the risk of nearby stars contaminating and biasing Cepheid brightness measurements, results using Webb data through the mid-2020s have generally continued to support the higher, roughly 73 km per second per megaparsec local value, reinforcing the sense that the tension is unlikely to simply vanish once slightly better telescopes are used, and strengthening the case that either new physics, an underappreciated local structure effect, or some more subtle systematic issue not yet identified, is genuinely at play. Beyond these already mentioned projects, several other planned and ongoing efforts are worth keeping an eye on. The Nancy Grace Roman Space Telescope, a NASA observatory expected to begin operations in the latter part of the 2020s, will carry a field of view roughly 100 times larger than the Hubble Space Telescopes, while retaining comparably sharp image quality, allowing it to survey enormous areas of sky efficiently, well suited both to mapping the large-scale distribution of galaxies for structure studies and to hunting down additional Cepheid variables and supernovae for distance ladder work. On the ground, upcoming next-generation cosmic microwave background experiments, including a planned successor, sometimes referred to under the working name CMBS4, aim to measure the faint polarization patterns imprinted on the cosmic microwave background with far greater sensitivity than Planck achieved, which could help further pin down the early universe side of the Hubble constant calculation and offer additional tests of proposed new physics solutions like early dark energy. Taken together, this pipeline of upcoming instruments, spanning ground-based and space-based observatories, Optical and radio and microwave wavelengths gives cosmologists good reason to expect that the picture will look considerably clearer within the next 10 to 15 years than it does today, even if nobody can yet say with confidence exactly what that clearer picture will show. One more thread worth including here, since it adds a genuinely interesting piece to the picture of what voids are actually like up close, concerns the handful of galaxies that do exist within them. Voids are not perfectly empty, they simply contain far fewer galaxies, spaced much farther apart than the denser filaments and walls surrounding them. Astronomers who have studied these so-called void galaxies, cataloging them through dedicated efforts sometimes referred to as void finder surveys, built from large redshift catalogs like the Sloan Digital Sky Survey, have found that they tend to differ systematically from galaxies found in denser environments. Void galaxies are disproportionately spiral galaxies rather than the smoother, rounder elliptical galaxies more commonly found in dense clusters, and they tend to be bluer in color, richer in gas, and more actively forming new stars, on average, than similarly sized galaxies elsewhere. The leading explanation is that galaxy mergers and close gravitational interactions, which tend to disturb a spiral galaxy's orderly disk, and often trigger the kind of intense star formation that quickly exhausts a galaxy's gas supply, transforming it over time into a smoother, redder elliptical galaxy, simply happen far less often out in the isolation of a void, where neighboring galaxies are too far apart and too gravitationally weak relative to one another for such interactions to occur frequently. In effect, void galaxies appear to evolve more slowly and more gently than their counterparts in crowded environments, quietly continuing to form stars from their own undisturbed reservoirs of gas, long after similar galaxies elsewhere have used up their fuel and settled into a quieter, redder old age. If the Milky Way and its neighbors really do sit within or near the edge of an unusually large local underdensity, this general pattern of quieter, less disturbed galactic evolution in less crowded surroundings offers one more small, tentative point of connection between the void hypothesis and the actual observed character of our galactic neighborhood. Though, as with the broader habitability speculation discussed earlier, it's worth treating as a suggestive detail rather than a settled conclusion. It's genuinely satisfying, and a little humbling, that a puzzle this significant remains open in an era when so much of cosmology feels settled and precise. The standard cosmological model, built from just a small handful of parameters, the density of ordinary matter, the density of dark matter, the density of dark energy, the geometry of space, the properties of the initial density fluctuations, explains an extraordinary range of observations with remarkable success. The pattern of the cosmic microwave background, the abundance of light elements like helium and lithium forged in the first minutes after the Big Bang, the large-scale distribution of galaxies, the growth of structure over cosmic time. And yet sitting right in the middle of all that success, and there's this stubborn 9% disagreement about one of the most basic numbers, describing how fast everything is flying apart. A disagreement that has resisted a decade and more of careful scrutiny by some of the best observational and theoretical minds in the field. Whatever the eventual resolution turns out to be, whether it's some overlooked measurement bias finally tracked down, some genuinely new physics woven into the fabric of dark energy or neutrinos, some combination of several smaller effects, each contributing a piece of the puzzle, including a meaningful but partial contribution from our own unusual local cosmic environment, or something nobody has yet proposed at all. The process of chasing it down is itself a quiet reminder of how astronomy actually works. Not through single dramatic discoveries that instantly rewrite the textbooks, but through years of patient, careful cross-checking, building better instruments, gathering larger and cleaner datasets, and slowly, methodically narrowing down the range of possible explanations until eventually one of them stands clearly apart from the rest. There's one more thread worth following before settling into a close, because it connects this whole story of local structure and cosmic measurement to something even larger, the very long-term future of the universe, and what future observers, whoever or whatever they might be, will eventually be able to see and measure, or fail to see and measure, from wherever they happen to be standing. The expansion of the universe, as best as current observations can tell, is not just continuing, it's accelerating. driven by the mysterious pressure of dark energy, which appears to make up roughly 70% of the total energy content of the universe, with the remainder split between ordinary matter, making up only about 5%, and dark matter, an unseen but gravitationally influential substance making up the rest, around 25%. Because the expansion is accelerating rather than merely continuing at a constant rate, sufficiently distant galaxies are, in a meaningful sense, moving away from us faster and faster over time, even though, at the local level, no galaxy is actually moving through space faster than the speed of light. It's the space between galaxies that's stretching, and there's no law of physics that limits how fast space itself can stretch, even though nothing can move through space faster than light. This subtle distinction between motion through space and the stretching of space itself was clarified through the framework of general relativity, and is one of the more counterintuitive but well-established features of modern cosmology. One direct consequence of accelerating expansion is that there exists what's called a cosmological event horizon, a boundary beyond which light from galaxies simply can never reach us, no matter how long we wait, because the space between us and them is stretching faster than light emitted from those galaxies can cross it. Galaxies beyond this horizon aren't destroyed or altered in any physical sense. They simply become permanently unreachable and unobservable from our vantage point, receding from our perspective, ever more faintly and ever more redshifted, until eventually their light fades entirely beyond detection, looking forward across enormous stretches of time. Cosmologists anticipate a slow but inexorable process of cosmic isolation. Within the next several billion years, our own Milky Way galaxy is expected to collide and merge with its large neighbor, the Andromeda galaxy, itself a slow, gravitationally driven process taking place over hundreds of millions of years, eventually producing a single, larger elliptical galaxy, sometimes informally referred to in advance as Milky Way. On a much longer timescale, stretching over hundreds of billions of years and eventually into the trillions, the accelerating expansion of the universe will carry essentially every other galaxy beyond the reach of that merged galaxy's cosmological horizon, leaving whatever future stars or structures remain increasingly alone, unable to see, detect, or communicate with anything beyond their own immediate galactic surroundings. Even the cosmic microwave background itself, that same afterglow of the Big Bang that current telescopes use to measure the early universe's expansion rate so precisely, will not last forever as an observable signal. As space continues to expand, the wavelength of that background radiation will continue to stretch, cooling and redshifting further and further, eventually stretching so much that it becomes indistinguishable from background noise. In principle, though this lies almost incomprehensibly far in the future, on timescales that dwarf even the current age of the universe many times over. In that far future, any civilization arising in an isolated galaxy, looking out at what remains of the observable universe, might see essentially nothing beyond their own galaxy stars, no evidence of the broader cosmic web, no other visible galaxies, no detectable cosmic microwave background, no obvious signature of an expanding universe at all. Such observers, however careful, and however capable their instruments, might reasonably but mistakenly conclude that their galaxy simply is the universe, static and eternal, because every trace of the universe's true history and structure would have receded permanently beyond their view. This far future scenario is speculative in its details, resting on assumptions about the continued behavior of dark energy that current data can't fully confirm over such enormous timescales. But it rests on the same well-tested physics, general relativity, and the observed acceleration of cosmic expansion. That also underlies the calculations discussed throughout this account. It's included here not as a dramatic flourish, but because it offers a useful, larger frame for thinking about the more immediate puzzle of the Hubble tension, and our own possible position inside a local void. Our view of the universe, at every era and from every vantage point, is necessarily partial, shaped by exactly where and when we happen to be observing from. Right now, in this particular era of cosmic history, we happen to be fortunate enough to have a genuinely wide window onto the universe's structure and history. Wide enough to detect the cosmic microwave background, wide enough to map the positions of millions of distant galaxies, wide enough to notice subtle disagreements between different measurement techniques and go looking for their cause. Future observers in a much more distant era may simply not have that same opportunity, through no fault of their own instruments or their own carefulness, but purely because of when they happen to exist. As it stands today, a great deal about this whole picture remains genuinely open. The precise size, depth, and boundary of any local underdensity in our cosmic neighborhood is still being actively measured and debated, with estimates varying considerably between different studies and different techniques. And no firm consensus yet on whether it's as large as the more striking estimates suggest or considerably more modest. The Hubble tension itself remains unresolved, with the gap between the early universe and local universe measurements holding steady or even sharpening somewhat, as measurement precision has improved over the past decade, rather than shrinking as more data comes in, which tends to argue against a simple, easily correctable measurement mistake as the full explanation. Whether the eventual resolution turns out to involve new fundamental physics, some refinement of our understanding of dark energy or neutrinos, some subtle systematic effect in one of the measurement chains not yet identified, some meaningful contribution from our own local cosmic environment, or as seems increasingly likely to many researchers in the field, some combination of several of these factors, each contributing a smaller piece, is a question actively being pursued by dozens of research groups around the world, using the newest available data from DESI, Euclid, the Vera Rubin Observatory, and the James Webb Space Telescope, among other ongoing projects. What makes this particular scientific story worth sitting with isn't a dramatic answer, because there isn't one yet. It's the quieter realization underneath it, that a measurement, as seemingly straightforward as how fast the universe is expanding depends, in ways scientists are still working out, on exactly where in that vast, web-like structure of filaments and voids we happen to be standing, and that even now, with satellites orbiting overhead and some of the most powerful telescopes ever built pointed at the sky, there remain fundamental things about our own cosmic neighborhood, the very region of space closest to home, that are still being carefully, patiently mapped out for the first time. It's worth remembering, too, just how young this entire field of study still is. In the broader sweep of scientific history, a little over a century ago, astronomers weren't even certain that other galaxies existed at all, let alone that the universe was expanding, let alone that its expansion was accelerating, let alone that its matter was arranged into a vast, web-like structure of filaments and voids. Each of the ideas woven through this account. Hubble's law, the cosmic microwave background. Dark matter, dark energy, the cosmic web itself was, within living memory of people still alive today, either entirely unknown or actively controversial. The fact that cosmologists can now argue productively over a 9% discrepancy in a single number, rather than over whether the universe is expanding at all, represents an enormous, if quiet, accumulation of careful observation and theoretical work across just a few generations of scientists. There's a reasonable chance that within the next decade or so, as DESI completes its survey, as the Vera Rubin Observatory's decade-long campaign gets fully underway, and as Euclid and James Webb continue gathering data, some of the open questions raised here will have clear answers. Perhaps the local void's size and depth will be pinned down precisely enough to calculate its exact contribution to the Hubble tension, whether that turns out to be a small correction or something closer to the full explanation. Perhaps early dark energy models or some other adjustment to the standard cosmological model will find decisive support or be conclusively ruled out by more precise cosmic microwave background measurements from upcoming ground-based and space-based observatories. Perhaps, as has happened more than once in the history of this field, the eventual answer will turn out to be something not yet seriously considered by anyone, some quiet oversight or some genuinely new piece of physics nobody has proposed yet, arriving as a surprise the way the accelerating expansion of the universe itself arrived as a surprise to most cosmologists in the late 1990s. Until then, the honest position, and the more interesting one to sit with, is one of patient, engaged uncertainty. The universe has given cosmologists a genuine puzzle, wrapped up in questions about where exactly we happen to be standing within its vast structure, and there's something quietly satisfying about a universe still willing to surprise the people, carefully measuring it, even after a century of steady progress. Wherever the resolution eventually lands, it will have come the same way nearly every other advance in this field has come. Through the slow, unglamorous accumulation of better data, better instruments, and better ideas, patiently sifted and checked against one another, until the picture becomes just a little bit clearer than it was before.